Hello, welcome back. This is Nagereza Alvin, uh, working with Mahanja Janet. I will inverse reinforced DQ knowledge distillation for credit risk prediction. So, uh, today's session, what you're going to talk about, we have introduction, related work, problem statements, research questions and objectives. We have the contributions, methodology, dataset description, the results, conclusions, limitations, acknowledgement. We're going to take you through how this work real quick. For the background and introduction. So accurate credit risk prediction is essential for minimizing loan defaults, at the same time maximizing profits for these institutions that lend money to borrowers. So the traditional credit risk prediction models that are used, they have limited ability to capture the complex patterns in the data. When the data is highly dimensional, the traditional credit risk prediction models, they find difficulty in capturing the complex patterns in that kind of data. So this makes firms incur losses to credit risk approvals that are given to the bad customers. These are the ones who default the loans. And while at the same time, these financial organizations, they want to be careful as they have to make profits, so they won't have to decline credit requests from good customers who repay and bring in profits. So what does this work do? This work aims at training a model that is more robust, that combines several techniques such as knowledge distillation, reinforcement learning, and deep learning. The model should overcome the difficulty that we've talked about, capturing complex patterns in high dimensional data in those traditional credit risk prediction models. The model should effectively operate in resource restrained environments, maintain its intended functionality to improve accuracy. Related work to this, so this work reviews the already existing research trends in assessing these credit risk financial institutions. So many recent studies are focused on solving the credit risk assessment problem. They are using various machine learning techniques. Most of them are using these traditional techniques, seeing the issue with those techniques. But while those techniques remain viable in assessing credit risk, most of the times they underperform when they are dealing with nonlinear data. So the credit risk assessment has evolved from the use of these basic or traditional credit scoring models to more robust techniques. These include knowledge distillation, reinforcement learning, deep Q learning, deep neural networks, among others. So moving on, the problem statements. So now, as we've seen, these traditional credit risk prediction models, their ability to capture complex patterns in the data that is highly dimensional is very limited. So it is limited, yet accurate credit risk prediction, as we've seen, it is an essential tool for minimizing loan defaults, maximizing profitability at the same time. So hence, there's a need to develop an efficient, robust, and more accurate credit risk prediction model for credit risk prediction, yeah, as we mentioned. So this approach is likely to face challenges. Now, for example, when data is highly dimensional, still you have to strike a balance and see how to maneuver it and work with high dimensional data, most especially for data for credit risk prediction. Most data sets, they have data that is always highly dimensional. And then at the same time, these data sets are always imbalanced in a way that the number of borrowers who are defaulters, they are less compared to these people who comply and pay back. This makes it difficult to support both claims in this case, and it may make the model become biased. So these techniques they also tend to be computationally expensive. So a real-time deployment might be difficult. The research questions and objectives for this. First, we ask what are the main comparative advantages for this approach compared to the traditional methods. Then, how can the continuous feedback loop, that is between the teacher and the student models, that is knowledge distillation, how can it be optimized to ensure adaptive learning and improved prediction accuracy in this assessment for credit risk? The objectives, we have to design a model that overcomes the difficulties that we've talked about for capturing complex patterns. Then we have to develop a credit risk prediction model that can effectively operate in resource-restrained environments while maintaining its intended functionality of accurate credit risk prediction. Then we have to minimize overfitting and underfitting these advanced techniques such as deep Q learning. So these are one of the computational problems as well. So research contributions for our work, we have evaluated our proposed credit risk prediction model against the existing solutions. We've demonstrated how accurate it is and its computational efficiency. Moving on, we've implemented advanced techniques such as knowledge distillation, deep Q learning, unlike the traditional techniques that face the difficulty that we've talked about. And we've implemented techniques such as SMOT to handle the largely imbalanced data sets. This is the methodology. As you see, we have the student and the teacher model. Basically, that is knowledge distillation. But what is this teacher model using to learn? The teacher model is learning by deep Q learning, which combines deep neural networks and Q learning. It has to output the soft values. In this case, it is outputting the Q values and the soft values, which it is distilling to the student model as the soft values. Now, the student model, instead of learning from the raw data, it is learning from these Q values or the soft values. After learning from them, it is believed to make better prediction. After making better prediction, it provides feedback to the teacher. This loop is continuous, so they can continuously improve each other. I'll stop here and let my colleague pick it up from here. Thank you.
Hello, my name is Manager Janet and I'm going to take you through the rest of our work about credit risk prediction. So this is our data set description and exploratory data analysis. We obtain our data set from GitHub. It has 12 features and 981 rows. So it just contains like borrower data characteristics related to loans and loan application. So this is just a table showing you some of the first rows in our data set. We have features like gender, married, marital status, education, and so on. So these features are a mix of numerical and categorical features. As you can see, loan status, which is our target feature, it has yes and no classes. That's a binary classification for credit risk prediction. Is a binary classification problem. We have property area, which has three classes: urban, rural, and semi-urban in other rows that you can see right now. Loan amount and loan amount term, those are numerical features, and basically this is how data set kind of looks like. This features a survey repayment patterns from like okay, there's a survey like borrowers applying for a loan and if they were granted the loan or denied. So let's move on. We have our output. So we trained a couple of this is about like the spread data analysis, sorry. These are just visualizations. We have a box plot of loan amount by loan status. So loan status, we have a yes and a no. And when it comes to the yes, which is a good credit risk for our case, we see we have a couple of outliers compared to those ones with the no. And because, I mean, that's because we have more borrowers in the yes class than in the no class. So we have a credit history distribution. That's the pie chart. So it's showing that 83.6% belong in the one class and the zero class has 16.4%. Again, this shows like it just signifies the imbalances in the data sets as we have more people with credit risk than those ones with bad credit risk. Comfort for self-employed, this is just the employment status. Want to know if a borrower is self-employed or not. And as you can see, most of the borrowers are not self-employed because they have the highest loan acceptances. As you can see, blue is for yes and the orange is for no. Applicant income, there's a start upload, showing applicant income, have a loan amount, and the hue is the gender. So the red data points represent males, blue data points represent females, and you can see most applicants earn between 0 to like 1,000 to 20,000 a month, and most of them have like a loan amount of between like 100 up to like 400. Yeah, but we have more males than females. Startup loan, this is for applicant income and dependents. And as you can see, some applicants don't have dependents, others have one up to like 4. So it's like well distributed. We have counted for property. So we have three classes in here. We have urban, rural, and semi-urban. And most people with credit risk are from semi-urban area, followed by urban, and then rural, as you can see. So this is some of the results we obtained after training our models on this data set. Our greatest performer is the graph neural networks, which has a 0.86 accuracy. And it also performed well across other metrics, as you can follow. Our worst performers were Q-learning and deep Q-learning, because they had a 0.5, which is like a 50%, and like 60% across other evaluation metrics. So yeah. Concluding, so with this study, we just want to like try to replace these traditional techniques used for credit risk prediction with more complex techniques like knowledge distillation, Q-learning, deep neural networks, such that we can capture these relationships between the borrower behavior, different borrowers, and make better predictions for financial institutions when it comes to credit risk. Some of the limitations we faced these robust techniques just require high computational resources such as memory and processing power. So they are just computationally expensive, and the data sets were very highly balanced. That's the biggest problem. More people with good credit risk and others with bad credit risk and this. So some of the feature works we want to have enhanced feature engineering, want to move to advanced data balancing techniques other than smooth, oversampling, another sampling, integration of these techniques. We want to integrate Q-learning, knowledge distillation, and reinforcement learning to come up with a well-compressed model that has stronger predictive power. So some of the acknowledgements would like to acknowledge our lecturer, Mr. Galiwangu, for the continuous support and feedback. It's really helpful. Plus our colleagues who inspire us more and really help us with different things with our works. Thank you. That's it for our presentation.